You'll end up in your transcript, right? Oops. I need to.
Guys, please scan the QR code and just register your attendance.
You'll end up in your.
A few people who are present physically are yet to come, and we'll start as soon as they come in. All right. Did you all scan? Okay, awesome. Ryan, you might want to like stop your speaker, or maybe use earphones.
Yeah.
Yeah. Welcome to the 11th workshop, the Transformers workshop, where we will be going in depth into how Transformers work and how they're made and also how they're used. Okay, so we will firstly be learning about Transformers, their architecture, and how they're trained. And after that, we will be going into Hugging Face, and we will also be talking about their use cases. Okay, so how are we doing this? Well, first, we are going to give you the big picture, right? We're going to give you an intuition of how the transformer works. And then we will also be teaching you the mathematics behind the transformer. Like we'll give you the formulas and all that. You don't have to actually remember them. You can just refer to them later, but you have to understand how the transformer works. And then we will show you how to use Hugging Face, and we will show you how to fine tune a model that you load from Hugging Face. So without further ado, let's move into it. Now, I want to go into the motivation of why we have transformers now. First of all, we had word2vec and ngrams, and those are essentially things that help turn words to numbers, because computers can't really understand uh, words, right? You can't just give computers words. How they understand it is by using numbers. So what word2vec and ngrams do is that they help turn uh, words into numbers. And after that, we had some models that try to do natural language processing, RNNs and LSTMs. And we talked about them during the last workshop. And now what we have is the evolution of the attention mechanism, right? Which is the transformers, which basically use attention. I will go into how they use attention later, but yes, so this is the overall history of how natural language processing has evolved. And all the models that you see over to the left side is actually models that are based on transformers, right? BERT, T5, GPT-3, and PaLM are all based on transformers. So why are they all based on transformers? Right? That is a question that we are hoping to answer throughout this workshop. Okay, so where can we find transformers? The most obvious thing, and something that you might already have heard of, is GPT, ChatGPT, and GPT-4, right? It's pretty famous, right? But did you know that Google has been using transformer-based models for a while? Well, Google has been using BERT, which is a transformer-based model that was trained by Google, and it has been helping them optimize search. That is why Google search has been it has been improving gradually, right? It's better than what it used to be, right? And now what people are saying is that they're using Gemini for their searches. Another interesting application of transformers is AlphaFold, right? where they use transformers to try to figure out how synthetic proteins that are made will fold into themselves. And this is really interesting and useful because it can help you make drugs, help you synthesize enzymes that are useful for bio. Oh, oh my God. Okay.
It's only after that part where I told you you weren't sharing screen.
Oh, I think the screen came in and just stopped the whole thing. Yeah, okay, okay. Uh, okay. Well, let me see. Okay, so I'll be going in and explaining about the transformer. We haven't explained the transformers yet, so you guys did not miss anything. Okay. And also, very sorry about the issues. I think we have some technical issues here. Now, what we have here is the initial transformer. It has an encoder, a decoder, and what it does is that it converts words to input embeddings because computers can't understand words, right? So we are converting them into numbers, and then we are sending it to something called multi-headed attention, and we will be explaining that. And after that, we will be sending them through the feed-forward neural network. Those are simple neural networks. And then the whole architecture is just multi-headed attention blocks and feed-forward blocks, as you can see, right? Okay, so what made the transformers such a powerful tool? Well, first of all, is the attention mechanism, right? Transformers use a special kind of attention mechanism, and which allows them to focus on the distances, the specific connections between words. The second one is self-supervised learning, right? Which enables them to learn more effectively than compared to what we previously had. And what makes transformers also special is the transfer learning part because they're very, very robust. And so you can adopt them to new applications by just fine-tuning like a small part of the neural network. So I will also be going through all of this. So just remember, we will first be talking about attention mechanisms. Second is self-supervised learning. And third is transfer learning and fine-tuning. All right? Yeah. Or NLP is where they're popular right now, but you can also use it for computer vision. You can also, as I showed you, you can also use it to predict protein folding. So it's like really, really useful for for problems where you have multiple things and you have to figure out the links between them and how each of these different things are connected with each other. So anything that's similar to like a problem where you like a language problem, right? You can apply transformers and try to like solve it. Yeah. If you guys have any questions online, please do feel free to ask. Okay. Okay. Okay, first of all, we'll be jumping straight into attention mechanisms. Now, so we have the transformer, and this is just a black box, okay? So the first thing that we want to introduce is the attention mechanism. So we want to introduce the encoder, the input embeddings, and essentially the transformer, okay? Okay, so let's first recap. What did we learn? And because some people were not present at last week's workshop, I want to recap a bit on embeddings and RNNs. And I will try to link them to why and how we have transformers right now. Okay, what are embeddings? Okay, so basically just you can think of it, computers understand numbers, right? So you have to convert words to numbers, and those are embeddings essentially. Okay, second of all is recurrent neural networks. A recurrent neural network is a network where you put in an input, and then you put in an input, initial input, and then you get an output, and then you feed it back into the neural network block, right? And you keep on doing it again and again. Wait, hold on. I will try to explain it as intuitively as possible. I know this is confusing, so just hold on for a moment, okay? Now, we have attention mechanisms now because the biggest issue with RNNs is that when you keep on feeding long words, what happened was that they forgot the initial parts of the sentence. So let's say that you have like a 10-word sentence, right? When you feed it, by the time you feed in the 10th word, it might forget the first 3 words or first 4 words, right? And that was a big problem for people who were doing research at the time. And attention essentially attempts to solve this by extracting outputs from each iteration of feeding the every time you put in to get an output from an RNN, you feed it into the attention mechanism, and it will help you like attend to certain parts of the sentence, right? Okay, wait, that sounds pretty confusing. Wait, I have a visual example. Okay, so this is an RNN, right? So what you do is you have a French word, right? Is it French? Yes. Okay. Now what you do is you put it into an RNN encoder. It generates a hidden state, right? And then you put the next word and the hidden state, right? And then you get the output, which is another hidden state. You add in a new word to the RNN, and then you add in the hidden state into the RNN, right? What happens is that the RNN is essentially adding more and more information to the hidden states, right? And then the final hidden state, the logic is that the final hidden state that they get can essentially be used to make like a translation, right? By using a decoder, right? Okay. Okay. A more easier way to think of it is by thinking of a game like the telephone game, right? Or like a game where you make people stand in line, right? So one person here, second person there, and what you do is that you like gives an information to the person, and the person draws on the back of the other person, and the person in front of you tries to interpret the drawing, and then they draw to the back of the person in front of them, right? Have you all heard of that game? Yeah. Okay. So think of that game. Okay. So first you have a person sending information, but what's different in this game is that you have people sending in information from the middle, right? So while this person gets the information, that person passes the information as a drawing, right? But no, another person comes in and sends them information to this person as well. So now the person has to combine this person's drawing and this information and draw on the back of the other person, right? So what's happening here is this. Oh. Wait, how do I hide this? Okay, so first you draw something, let's say like a part of the house, right? And then the person tries to draw it on the back of the person, and the next person interprets as this wobbly thing, right? And then you tell the person, put a roof on the house, right? And then the person puts a roof on, they don't know it's a house, right? They put a triangle on top of it, right? And what happens is that when they draw it on the back of the other person, what happens is that it again gets distorted a bit, right? And then when that person will be asked to like add a sun, right? And that keeps on happening. But what you can see is that the image is being altered bit by bit as it passes on from one person to another, right? So that is what essentially happens in an RNN. The information gets distorted, okay? So, which is why it might forget information that was essentially put into the network. Okay, so what attention tries to do is that it tries, hello, yeah. I'm sorry if it's confusing, but like, yeah, just try to listen. Okay, what attention tries to do is that it gets the output of each iteration of the RNN, right? And then it tries to figure out which information is the most important, and then tries to get, and then the output of that is sent to the decoder for every sentence that it produces, or every word that it produces. So in a translation task, what that means is that it'll get information from all the words, as opposed to just one output, right, from the RNN encoder, and it sends it to every single decoder block that's there, okay? Okay, but then why, right? Why do you need that? Why get information from the middle of these RNNs, right? Why not just convert these words to numbers and just put it straight into the attention mechanism, right? Well, that's what the researchers thought, and that's why the paper is called Attention is All You Need, okay? So, again, so attention is all you need because the RNN is just an extra step, right? If you can figure out how to turn the words to numbers as effectively as possible, then the attention will just essentially figure out what sentence was more important for the translation task, and then enable the decoder to translate the sentence to a new language, right? Okay, hope that was clear. Okay, so now we have attention. Okay, all right. Okay, so this is a diagram that shows you how this task can be somewhat complicated, right? So here, what we are doing is that we are converting a sentence in one language to another language. If you guys, the guys who are online, please let me know if you can see me like point at things, okay? If you can't, just let me know, okay? Okay, so here we have a sentence in one language, and when it gets translated, right, you can see the attention mechanism is paying attention in a somewhat different way here, right? And that's because the order of the words have shifted here in when they translate to the other language, because that's how the semantics of that language works, right? And here you can see it's also weird again. Why is that? Because two words represent one word over there, or no, three words might represent one word, like two words over there, or and so on and so forth, right? So it's a complicated task, right? But the attention mechanism can actually help in figuring out how to figuring out all these nuances in the language, because you are getting you are trying to prioritize what's important, right? Okay, so this is another example of how it pays attention. This was supposed to be a GIF. It's okay. I mean, it essentially tries to convey what's in here, so that's fine. And so this is the paper. Attention is all you need. Now, okay, so what we have here is why now we figure out why we have attention-based and attention-based architecture. Now let's figure out the construction of the architecture, all right? So what is the first part? Well, the first part is the input embedding. Okay, so the first major block is the encoder, and the encoder has multiple components. First one is the input embedding part that translates the words to essentially numbers, right? And then you have the multi-headed attention part. Okay, so what does the input embedding part do? It converts the words to numbers, words to vectors, essentially. But on top of that, in a transformer, what it does is that it adds in positional encoding. So a transformer is not does not care about the order of the words. Okay, it only cares about the relationship between those words. So what the researchers did was that they tried to come up with a way to figure out to let the transformer know the order of the words. And what they did was that they added positional encoding to the input embeddings that they got to get the positional input embeddings. Okay. So how did they do it? Well, they use this function, the sine-based and cosine-based function. So if it was even, they use the sine-based function, and then they use this to basically get the positional encoding. And then they use the cosine function if it was odd, right? And why they chose this is because it helped give linearity, because it had properties that can help learn the transformer model. If you guys want to know more about it, you can go online and read it. So this is basically the math, which is, I mean, you can refer to it later if you want to, right? But what I want you all to know is the intuition, because that's what you guys are going to remember, right? If you ask me this equation, I wouldn't remember in like 2 or 3 weeks, right? So now the next part is the multi-headed attention. Okay, let's break this word into two. Okay, one is multi-headed. What is multi-headed? I'll get to it. Okay, and then attention. Okay, this applies a mechanism called self-attention that allows the model to associate each word in the input to other words. Okay, it is also possible that the model learns that word structure in this pattern are typically a question, so responds appropriately. What does that mean? Well, the attention mechanism helps figure out how the word works. Okay, so based on the order of the letters, so now we have the numbers for the corresponding words, and what you do is you take those numbers and put it into the attention mechanism, and the attention mechanism essentially tries to figure out the relationship between those words. Okay, so the first part of the attention mechanism involves, well, something called query key value. Okay, let's look at it again. I don't know if I can pause it, but yeah, let me see. Okay, never mind. Okay, so what we have is, yeah, so what we have is the set of words that have now the set of vectors that represent the words and have positional encodings. And what you do is make 3 copies of them. Okay, so they're identical, and then you send it through a linear layer. Okay, so you send it through a linear layer, and the linear layer adds changes to it. Okay, and that can be trained when you're training the neural network. And what you get is 3 different parts, right? And essentially, initially they were the same, and when you send it through the neural networks, they get altered, and you have 3 different matrices of identical dimensions. So what you do is you take query and key, right? you do a dot product between query and key. Well, wait, what does that mean? Well, you get query and you get the transpose of the key. The transpose operation basically just changes the vertical columns to horizontal horizontal rows. Okay, rows. So what you have is query gets multiplied by key, and you get this square matrix, right? With attention values. So all the numbers within the matrix gets multiplied, and you have this square box. Now, this square box, you do certain things to it. Wait, hold on. Okay. So what this square box is trying to emulate is the attention mechanism. Okay, so it's trying to figure out. So when you multiply the numbers, these matrices, right, that are different, are now being multiplied, and you have this square matrix that shows the importance of different words with respect to other words in the words that you put into the model, right? Right. Now, what they do is they alter the numbers. They scale the numbers by using the square root of the dimension of the model, the dimension of the matrix, right? And then you get the scale scores, right? You scale it by using this number. It's just a number, okay? So you just divide all the numbers here, okay? And then you apply a softmax function. I hope you guys know what softmax function is. We taught it during last sem. Okay, essentially what it does is that along every column, the sum is going to be 1. Essentially, it's like a probability distribution. You can think of it as like a few probabilities. Okay, what you do after that is that you have this value vector, right? And then you multiply this value vector. You have this value vector, and you multiply this value vector with the scores. Okay, so that is what I will be showing in the equation, in the next equation. Okay, okay, so this is the equation that represents attention. So all of that complicated stuff is now like compressed into just symbols here. Okay, so let's try to break it down. Okay, Q is the query, K is the key, right? And you can see key represents the transpose operation, okay? And then you divide it by the dimension, right? So that's called scaling. And then you apply the softmax function. So what you have here, essentially, is the softmax function, right? And then the output that you get, the square that I hope you guys remember, right? The softmax value, you multiply it by the value matrix, right? The value matrix that you saw in this slide. Okay, do you guys understand? Is that clear?
Okay, so attention is the intuition behind it is just you just try to find the most important word or words inside a sentence. And
Yes.
focus around it.
Okay. Yes.
And then how is you said that they go through like linear layers?
Yeah. There's a linear layer in the middle. Yes.
So where does the linear layer come from?
Linear layer essentially puts there's a linear transformation on the matrix, so it's part of machine learning. So basically, linear layer basically changes it by a number, like multiplies it by a number, and it's called weights and biases, right? Yeah. And how do we know the linear layer, right? I think that's your question.
Yeah, because it is like you want to train this model, but
Yeah.
to train the model, you have to train another model.
Yeah.
Yeah.
Okay, so the fun part is that this linear layer is first randomly initialized, and then when you train the whole model, the linear layer also gets trained. And what they're hoping is that this thing will turn out to show how the model is attending to the values. Yes. Yes, basically. Is that clear? For those of you who are online. Okay. Is everyone okay? Yeah, okay. All right. Awesome. Okay, so what's multi-headed attention? You can think of it like this. They're essentially breaking down the vectors, right? And then they're sending it through multiple pieces of that self-attention mechanism, right? And then they're getting the output, and then they're just fusing them back together. Okay, essentially that's what's happening. The intuition is that the hope is that if you do this, right, it will learn different kinds of things about the sentence. So let's say that one head learns about whether the sentence is a question or not. Another head learns about whether the sentence is showing happiness or sadness or something like that. I mean, it's not explicitly that, but then you can think of it like that. Okay, so that's the intuition here. So the feed-forward neural network is the next part. The feed-forward neural network has I believe 2 linear layers and 1 ReLU function. It's basically like a simple part. It's much simpler than the attention mechanism. And unlike the attention mechanism, where you send all the vectors, all the numbers essentially, into the attention mechanism together, the feed-forward neural network can you can send the output values through the feed-forward neural network individually, right? So you can have like parallel, like all the vectors can go through the feed-forward neural network parallelly. So that's one advantage that you have because of this simple part. Now, so what we have now is we have the input embeddings. We know how we get the vectors. We know how we add position encodings to it. And then what we get is we get 3 copies of it, send it through a linear layer. And then you multiply query and key together, the transpose of the key together. And then you alter it to some, by some value, right? And then you put softmax to it, right? And then the output that you get is a matrix, and you multiply the matrix by the value, right? And then you send it through the feed-forward neural network. So that's basically the summary that we have here, okay? Next, this is the equation for multi-headed attention. So what this is trying to represent is that you are sending it through the attention mechanism, but you are sending it after you split them to like multiple matrices. The queries and the keys and the values are split into like multiple matrices, and the hope is that they will learn different kinds of information about a given sentence or about a given a sequence of information, right? Okay, so you heard 2 different words. You have 2 different words here, okay? One is attention and the other one is self-attention. Attention is what you use in like RNNs and all that to pay attention to things. But what we have in a transformer is slightly different. It's called self-attention. So what's the difference? Well, attention basically tries to figure out the importance of certain words. It pays attention to certain words in the sequence, right? While self-attention tries to figure out the connection between the words in the sequence, right? So that's the difference. It's subtle, but it's actually pretty distinct because it tries to figure out, you can think of it like in a 3D space, right? What it's trying to do is it's trying to figure out the least distances between the words, right? It's trying to arrange the words in 3D space, essentially. Okay, and I want to tie it back to the CNN workshop that we did. Okay, so attention, multi-headed attention, right? You can think of I'm trying to like link it together, okay, so that you guys remember. So in CNNs, you use like multiple different kinds of filters, right, to extract information. What attention does is it's trying to figure out the like the information on different parts. I mean, the connection is not that much. I'm just trying to like link it back together so that you guys remember. Okay, so they're trying to figure out basically the distances between the words and the how each words are linked with each other, right? Okay, so that's it for the attention part. So do you guys have any questions? Anyone online? People online? Okay.
But you answer it just now.
Oh, okay.
Just say it again now.
Okay. So basically, self-attention. Okay. Multi-headed attention and self-attention are two different things. We'll hold on. Okay. Self-attention basically tries to figure out the link between different words, right? And multi-headed attention is you get the numbers, the vectors for each word, and then you split the vectors, and then you send it through multiple attention mechanisms, right? So multi-headed attention is very different from self-attention. Self-attention tries to figure out the link, the connection between different words, while multi-headed attention is the act of sending your word vector that is split into multiple parts through the attention mechanism. So those are completely different things. Does that make sense? Okay, awesome. Okay, so next is the training part. Okay, the way we train transformer-based networks is called self-supervised learning. So you guys have heard of supervised learning, unsupervised learning. Oh, what's self-supervised learning? Well, it's slightly different. Like there's okay. First, I'll explain how this works. Okay, I'll explain how the self-supervised learning mechanism works. First, you have a sentence, right? Let's say you have, my name is Sylvian, right? So yes, that's from Hugging Face. It's from one of their workshops. Now, what you do is you take the first word, you hide all the other words, right? And then try to make it predict the second word, right? And the ground truth is the second word. You already know the second word, right? And what you're trying to do is you're trying to make the transformer predict the second word. Okay, and then what you do is you reveal the second word, right? And you cover the rest of the word. So you cover the last two words, right? You show the model the first two words and say try to predict the next word, right? And that is right? And you keep on doing it, right? So that's one way of training the model, right? Another way of training the model is called masking. So what you do is that you have a sentence and you remove certain words, right? And then say, oh, figure out what should go in like between the brackets, right? Essentially, what you're trying to do is you're trying to make the neural network figure out what goes within the brackets, right? But you already know what goes in within the brackets, right? So you can make a loss function out of it, and you can say, oh, if you predicted badly, then the model will say, oh, it's wrong, right? And then that will get fed into the transformer, fed into the training mechanism, and it will correct itself, right? So we have two different ways of training the model. One is by making it predict the next token. The second one is by masking. There are other methods too, but I won't be going into it. So why is this special? Well, in supervised learning, right, usually when you train a simple neural network, I don't know if you guys have tried training the MNIST database, right? So when you train the data set, what you have is an image and then a label, right? Usually, when you're making the label, what you need is human input, right? Usually, people are involved in making the label, and that's time consuming and it requires more effort. Okay, so how self-supervised learning is different is that you don't need humans to do the labeling, right? Because the input itself is the ground truth, is the label, right? Again, let's do normally in supervised learning, you need labels, and humans give you labels. And this one does not require labels because the sentence itself, the words in the sentence itself, is the label, right? So that's the difference. So that means that if you can get enough sentences, if they're clean enough, what you can do is you can immediately start training the transformer. You do not have to pay humans to do it, humans to get labels, and that makes training somewhat easier compared to other models. But there are caveats. there are challenges with the transformer-based model. The biggest challenge is that it's data hungry, right? So you have a lot of parameters that you need to train. And to train them, you need to have a lot of, okay, let's say that you want to train them to be as good as GPT-4, right? To do that, you need millions and billions of words, of sentences, so that the model can learn, because the model itself is huge. So when you have a lot of parameters, what you need is that you need more more data to actually train the model, right? The second problem, the second biggest issue, is that people don't understand that how the transformers work, how these mechanisms work. So I think we can get link it to the question that you asked, right? So we are putting it through the linear layer, right? But like, how does the linear layer know that you are training it for attention, right? How does he know, right? Yeah. So there are questions like that, and then there are like one of the people who were part of the Google Brain team left because when he saw like ChatGPT and he heard that it was because of transformers, he thought, oh, this can possibly be called AGI, right? I mean, there are like different researchers can't essentially figure out how these transformers work, and that's the point that I'm trying to make. And the last one is biases, right? Okay, so we are inputting texts that are there on the internet, right? We are putting texts that are publicly available, right? We are putting texts that were written by human beings, right? What happens is that people have biases, right? So when you train the neural network on texts that have biases, what the neural network is going to assume, what the transformer is going to assume is, oh, then it's okay to say stuff, say specific sentences that might be biased towards someone's religion, someone's gender, someone's identity, right? And so on. So these three are the biggest challenges with the transformers. There are three different kinds of transformers that are currently in use. Initially, I showed you the model. Wait. Okay, so the transformer has two big parts, right? One is the encoder, and the other one is the decoder, right? So there are transformers. There are three different kinds of transformers. One is the encoder only transformer that only uses the encoder part, right? And the examples for such transformers are BERT. BERT is by Google. Roberta is and DistriBERTs are like variations of the BERT architecture. Now, the second one is the decoder only architecture. And for decoder, I'm pretty sure you know what these are, right? GPT-2, GPT-Neo, and GPT-3 are by OpenAI. They only have the decoder, right? They do not have the encoder. And then you have the encoder and decoder models that are BART, T5, and Marianne, right? And they're used basically for translation, summarization, and generative question answering. So yes, so we have three different kinds of transformers currently. Okay, now that we know, right? We know that the biggest issue and the biggest reason why we won't be teaching you how to make a transformer from scratch, right? We are not planning to do that today, is because of this new paradigm that we have today. We know for a fact that transformers are very data hungry, right? That means you need a lot of data and you need a lot of computing power to actually train the transformers, right? So to get a pre-trained language model, right, you need multiple days of training and a very large corpus of data that has been cleaned, that has been looked for, and people have to look at it, monitor it for biases and stuff. And then you need a lot of money, millions or even billions now, right, to train these models. So normal people like us can't really afford to do it, right? If we are doing it for like individual purposes, right? But the good thing about transformers is that you can adopt these existing models. that are trained on human languages, human corpus, right? And then you can you can fine tune it for a specific task. Okay, so that is what we will be going into. Okay, so these pre-trained models, to fine tune them, you do not need as much compute power as, let's say, training like a model from scratch, a pre-trained model from scratch, right? And then you can easily reproduce you can easily reproduce the results, and also you do not need a huge database, right? If you have your specific database, it already understands how the connection between languages, the meaning of languages, and how to generate words. So what you have to do is just you have to take your specific data set, and you can train it to understand those understand that specific data set. Okay, which brings us to transfer learning and fine tuning. Okay, so we won't be training you how to make a transformer from scratch, but there are resources online for you to maybe test it out, like really small models that you can try out, but they aren't as useful they are not at all comparable to what we have today, like GPT-3 or GPT-4 or Gemini or whatever, right? So what we will be doing now is we will be learning about fine tuning, okay? And we will also be talking about a really useful something called Hugging Face, a tool called Hugging Face, okay? Okay, so Hugging Face is essentially the attempt of people in the public domain to solve these three big issues. So essentially, when we are using models, right, like the latest models are first published as research, right? So those research papers had a lot of problems, right? Until very recently, they had a lot of problems. They had bad documentation, so they didn't know which Python to use, which version of PyTorch to use, or which version of TensorFlow to use. And if you guys have tried um, implementing some of those research papers, you know that it's a horrible experience, right? And then some of these research papers, even if they provided APIs that you can call on, right? They had issues like they sometimes they didn't respond. They had issues like they were not tested properly and things like that. And then also on the public domain, you had multiple versions of models that were based on foundation models, right? Like BERT, there are like variations of BERT, and it can be very confusing to figure out which one you want to use, right? So the tool that we have, Hugging Face, tries to solve all of them, right? Well, okay, so what we're going to do is we're going to try to go to huggingface.com, right, and see what features are there, what facilities are there, and then we will be talking about fine tuning on Hugging Face. Okay. Okay, I'm going to stop presenting now. Hold on. Okay. So this is the Hugging Face website. Is there a way to? Okay. Okay. So can you see it? Okay. So this is the Hugging Face website. So here you have different features. So what I want to focus on is the model tab here. Okay, the model tab over here. So if you go there, you have multiple different kinds of things that you can find on Hugging Face. So there are models that are specifically made for feature extraction, text to image, right? Converting text to image like DALL-E 3 stuff, and models similar to that. You have image to text, which tries to give you a description of like an image that you put into the model, right? And then you have multiple different categories of models, right? So you can try choosing one of these. Let's see anything interesting here. Wait, hold on. What happened? Oh, okay. Natural language processing, that's what we are doing now. Let's choose the first option, text classification. Oh, okay. So as soon as you choose it, what it gives you the options of different models that you have. And then what you can do is, okay. And then you can go and try to find out like a model, a specific kind of model that you need. Okay. So let's just click on the first option here. In here, you can actually like test out. In here, you will have like the name of the model. Please keep a note of that, the name of the model. And then you have a description of the features of the model. And they might even give you like code examples of how to run the model, right? On the right, on the left side of your screen. On the right side of your screen, they have a small API that you can use to test out the model and see if it works. And you can just try it out before you put it into you try to use it. Okay. So you can just put the input and then click compute, and yeah. So that's basically it. Okay, hold on. How do I extend this? Okay, awesome. Okay, so now we know about the Hugging Face website. We know that there are models that you can test out and try out, and those models have specific names. And I wanted you all to make a note of them because you can, when you're using it, when you're trying to use Hugging Face in your code, right? You will need to know the name of the model. Okay, so let's jump in and try to see how we can fine tune. Okay, so before we go into fine tuning, there's also a useful resource by Hugging Face, Hugging Face, right? So what I essentially did was the fine tuning part. A lot of it is from here because I mean the instructions were pretty good. I altered some of it so that I can explain some stuff better, right? But if you want to, if you don't understand, you can go here, just go to Google and say Hugging Face and then transformers and then fine tune a pre-training model, and it'll give you like a proper instruction. And also what you can do is you can press open collab, right? And then there are 3 different ways that you can use to fine tune. One, the mixed one is provided by Hugging Face. So you can use the Hugging Face API itself to fine tune. The next one is by PyTorch or TensorFlow. So based on your preference, you can choose PyTorch or TensorFlow. It doesn't matter. You can fine tune the model through that. So basically, if you click here, it'll give you a Colab that you can try out and you can try running it. Okay. Why is it so slow? Okay, awesome. I think there was an issue with the internet. Okay, so this is the Colab file that you can go through. There are pretty much like they have instructions and YouTube videos that you can go to. So what I'm going to use is I'm going to use a slightly modified version of this to explain you all how to fine tune a model on Hugging Face. Just give me a second. Controls. Okay. All right. Okay. So let's just dive into it. Okay. Okay, the first part is code that I have included. I have added to the code provided by Hugging Face. So beyond this point, beyond fine tuning a pre-trained model, It's all by Hugging Face, okay? I'm just going to explain to you how it works, right? But before that, I will go step by step and show you like what I've added, okay? All right. Okay, let's try running this. Runtime. Okay, so before you run anything on Google Colab, what you have to do is you have to choose a runtime. I think you guys already know this. I'm choosing a GPU runtime because machine learning models can run faster on a GPU, right? And then I'm going to run this whole thing. Okay, first. First of all, we are installing transformers and data sets. Okay, those two are by Hugging Face. Okay, so we will be calling transformers to load our model and to train our model. Okay, later on. Now, I think that's done. Okay, so Hugging Face, right, gives you an easy way, has a simple and dedicated AI for several tasks, like masked language modeling, sentiment analysis, speech extraction, question answering, right? So Hugging Face gives you an easy way to load a model, right? And then you can run inference of it very easily within 2 or 3 lines of code, okay? So I'm going to show that to you here. Okay, so what we have here is from transformers import pipeline. So we are going to Hugging Face, right? That's transformers. And then we are importing the Hugging Face pipeline, right? After that, what we are going to do is we are going to use the pipeline to load a sentiment analysis model, right? So if you put sentiment analysis, what it's going to do is it's going to load the default model, right? For analyzing sentiment that's given in the Hugging Face website, right? So now that you have loaded the model, what you use is you send a set of sentences, a bunch of sentences. We are very happy with the workshop. I hate this workshop, and the workshop was neither good or bad. Okay, and what we're going to do is we're going to run it. We are going to send it through the model, right? The model is represented by the classifier. It's provided by Hugging Face, right? And you get the results, right? And then what we're going to do is we're going to print the result and see what Hugging Face thinks uh, about these 3 sentences. Okay, so the sentiment that is represented by the first sentence is that we are happy with the workshop. That just shows a positive sentiment, right? So that's why it's called positive. And the other 2 are somewhat negative. For some reason, I think the last part is also negative. Okay, but yeah, so what you can do, as you can see, all you need is just 2 lines of code to get an output from a specific model. And that is not how it used to be, right? It was much, much more complicated to get a model and to run a model. And right, Hugging Face has simplified it so much for people who want to implement, who want to test out models or who want to try fine tune those models. The next thing that I want to show you is talk about the Hugging Face Model Hub. I went to the Hugging Face website and I showed you that there are a list of models that you can use, right? So what we are going to do is we are going to import auto model for sequence classification and auto tokenizer. You can go to the auto model site and see what it does, right? Wait, hold on. Sorry, wrong one. I put the link here somewhere. Okay, I might have missed the link. Okay, it's okay. I can go. Okay. All right. So here is the documentation. Please, if you want to try out new things in machine learning, you shouldn't be afraid to go through the documentation, because that has all the instructions that you need to learn about something, right? So what we are using here, wait, hold on. What we are using in our Colab is called Auto Model for Sequence Classification, right? Okay, so let's try to find that, right? In the Hugging Face website. Okay, I'm going to just copy this. And I'm going to try to find it here. Okay, so here in this website, you can find out what Auto Model for Sequence Classification does, right? So what you have is, it tells you what it can and cannot do. Okay, so so what you have to do is, if you want to do try something else out, what you have to do is you have to go and figure out from the Hugging Face website the different models, different types of models that you can load, and different actions that those models can do. Okay, now let's get back to the Colab and let's try running this first. Okay, so what's different here? Okay, first I got the name of the model, right? And the model that I am using is called DistilBERT, Base Uncased Fine-Tuned SST to English, right? So DistilBERT is a variation of BERT that was made by Google. It's a smaller model, right? And it has less parameters. But I'm using it because it's easier to load onto Google Colab, right? And then it's an English model and it's a base model, but it's fine-tuned. Okay, so if you want to go, you can find we're using text classification. So you can go here and then you can get a copy of this, and you can come here and put it back into the model name, and then that's it. That's how you load a new model. So okay, so I'm going to go back. So what we have done is we have gotten the model name, and we have loaded the model by using Auto Model for Sequence Classification, right? We have given the model name, and from pre-train, what it does is that it loads the weights of the model, right? So Auto Model for Sequence Classification does not load the weight; it loads the correct type of model, right? The model is for sequence classification, right? It's in the name, okay? And this loads the weights of the model, and now you have the model, right? And then you need the tokenizer. Why do you need the tokenizer? Well, you need the tokenizer to convert words to numbers, right? Okay, so now that you have the model and the tokenizer, again, you need to use from pre-train, but because you need to load the weights, right? You can send the okay, so you can put it into the classifier. You can define the classifier using pipeline that we loaded before here, right? And in the pipeline, you can say what kind of task you want, which we used here, right? And then you can also put in the name of the model. So if you put the name of the model, what it will do is that if you want to load the default model, it will load the specific model that you asked for, okay? And then you also give it the tokenizer that you loaded. And again, the tokenizer, it will use the specific tokenizer that you asked for, right? So the pipeline has the model and the tokenizer, it's all combined. You do not have to code anything. You just have to use the pipeline. And what you have is you can input an array of sentences, and what it will give is the results. And here are the results. So the first sentence that we inputted is that we are very happy with the workshop. And the sentiment about of that word is that it's positive, right? Because it says happy, right? So happy is often associated with a positive sentiment, right? And then I hate this workshop. Hate is associated with a negative sentiment, so it's negative, right? And you can even see the score that the model has given to the sentences. So if you want, I can try to change it. I have a green car. and we can try running it here. Okay, so okay, for some reason it thinks it's positive, but okay, so okay, for some reason it thinks it's positive, but sometimes you can get outputs where it's not exactly 99% accuracy. It might be like a very low kind of accuracy because it doesn't know if it's positive or negative. It might be some neutral word and it might be confused, and the model might not give you, an output and say it's positive, but then the score will be somewhat lower, right? Compared to something like explicitly like we are very happy, right? Okay, now let's try to see what the tokenizer does. Okay, first, we are going to use the tokenizer to tokenize this sentence. Okay, and then we are going to try to get the ID of the tokenizer. So what the tokenizer does, as we know, is that it converts words to numbers, right? And we are trying to see what the numbers are like what the numbers are for each words. And then we are trying to see what the input is, right? Okay, so I've printed it here. We can run it again if you want. Yeah, while it's running, so these are the words and these are the corresponding numbers that are given by the tokenizer for those specific words, right? Okay. Okay, so now a bit of PyTorch. Okay, we're just gonna see how this whole process is going to work if we try using PyTorch as opposed to Hugging Face, right? So we are going to first load import torch and import torch in an functional. You can search online on what it does specifically. I just want to quickly show you how this works. Text. So for text, we are inputting an array of 2 sentences, and we use bash tokenizer to basically tokenize the whole thing, right? So we are going to give it a padding so that if the basically if the max length is not reached, it'll add some padding to it. If it's too long, it'll truncate it, it'll cut it. That's called truncation. And then we say return tensors as PT. So PT stands for PyTorch, right? So it's going to return PyTorch tensors. Okay, so with torch no grad, right? So what no grad does is that it removes the gradients, right? And now we are trying to get the output, right? So we need to use 2 stars. I mean, it's PyTorch. So what I'm trying to show you is that it can be, you need a lot more lines of code to actually use this, right? You can get the outputs, and then you have to apply softmax to the logics of the outputs, and then you can print the predictions, and you can print the labels for those predictions. And yeah, so all of this, right? I will run it right now. All of this to show these 2 labels. Okay, all of that was done within just 2 lines here. As you can see, it'll give you the label, and it will also give you the corresponding score for that label. Okay, so now we know how to get the model, right, from Hugging Face, right? All we have to do is just copy the name of the model, and you can use Hugging Face pipeline to load the model, and then you can just run, you can just give it inputs, and you can get outputs from it, right? Okay, so let's get to the important part, fine-tuning a pre-trained model. So this part is from Hugging Face. Okay, I just used it because, well, it's pretty good. Okay, and if you guys have any questions, you can simply just go and check out the YouTube videos. You just have to play it. Okay, first, what we're going to do is we're going to import data sets, right? And the name of the data set is given inside. It's called Yelp Review Full. So Yelp is like a site for reviews, right? And what they have done is they have loaded some of the reviews, right? So as you can see, my expectation from McDonald's are really high, but for one to still fail so spectacularly. Okay, these are reviews. Okay, these are reviews of different things. Okay, so now that we have loaded the database, right? Hugging Face makes it really simple. You have to use database data sets, and you can easily load the data sets. Okay. And from transformers, again, it's from Hugging Face. You use auto tokenizer to basically tokenize all these words that you have now gotten from the data set, right? I can run it now. And you can say, oh, so basically you're tokenizing it here, and then you get the tokenized data set and save it here. Oh, wait, I think I missed something here. Oh, saving the data set. Okay, I will get to it. I'll let it run for a bit, okay? It might take some time. While it's running, I'll try to explain the rest of the code here. Here we are preparing the data set. We are splitting it into train data set and test data set, as you do when you want to train and test, right? Fine tuning is essentially that, like training. You need training. You need a test data set and a train data set to test the. A train data set to train the model, because your fine tuning is essentially training, right? It's just that you are not completely training from scratch. You are using an already trained model and you are improving it for your specific task, right? And then the test data set is for testing, essentially. Okay, so again, what we are doing is that we are getting the auto model for sequence classification. And here, what we are loading is BERT base case, right? And then what we are going to do BERT is again the model by Google. And we are going to use, this is one of the dependencies that this needs, which is why I am using, sorry about that. Yeah. And then you can use the transformer. Transformer like gives you the ability to train, so you do not have to use PyTorch to train it. But if you do want to train it using PyTorch, the code for that is given on the Transformers website, the Transformers link that I showed you. So basically, with just 2 lines of code, it takes your data set, takes your model, tokenizes the data set, and then it just trains it. Okay. So all of it is just done with just 2 lines of code. Tokenization is done before, but yeah, this part does the training. And then what you have to do is you have to evaluate. Let me see if this is done. Okay, it needs a bit more time. Okay, so to evaluate the model, we are installing evaluate, right? And then the evaluate library is being used here, the Hugging Face evaluate library from Hugging Face. What we do is we import it, right? And then we give the metric, and the metric is accuracy, right? And then we are going to evaluate the model, right? Now, after giving the evaluation metric, what we do is we go on to the next one. We yeah, I shouldn't have run it.
How's it in?
Sorry.
How's it in?
It was okay, I guess. Wanted to show you how to save the model. Is it done? Oh no. Oh my God. Okay. I'll try to give you an explanation. It's going to take too long for that to like load. So what it's doing is basically it's tokenizing everything. Yeah. Where was I? Okay, I was here. Okay, so now that we've imported evaluate and given it a metric, what we do is we use. Okay, so we basically we are basically trying to calculate the accuracy of the predictions, right? So we have to convert um, the prediction to logits first, and then after this, what we have to do is we have to like monitor the evaluation metrics, right? So for that, we call the training arguments and the trainer, and into the training arguments, we put test trainer, and the evaluation strategy is epoch, which is commonly used in machine learning, right? And then into the trainer, we put in the model, right? For arguments, we put in training arguments. And for train data set, we put in the training data set that we use to train. And for evaluation data set, we put in the evaluation data set that we split into train and evaluation testing data set, right? And then and then we put in compute metrics, which we initially uh, put, which we initially defined here, right? So the compute metric define how to calculate the accuracy of the predictions. And then you run the trainer, which basically trains the model. And then you can save the output of the trainer by using the save model. And then you can save it to the directory that you initially defined here. Okay, this is almost done. Okay, okay. Before we run that, I want to go through like a small recap of what we learned today. First of all, okay. First of all, we talked about the attention mechanism, right? We showed you how words are first converted into numbers, and then those numbers are used together to figure out how they're related between each other using the attention mechanism. And after that, what we did was we sent them to the feed forward neural network, right? And then we talked about, okay, and then we talked about self-supervised learning and how it was different from supervised learning, and how you can use the input itself to teach train the model, right? And then we talked about transfer learning and fine-tuning, and why it was more important to learn about fine-tuning and not about designing a transformer from scratch, right? Okay, something happened. Okay, when I tried it out, it worked. I don't know why it's not working. Okay. Yeah, okay. There is an error. I had it last time, but I fixed it, but it's here for some reason. I mean, I got accelerate here. But yes, so after that, we learned about Hugging Face library. Okay, we learned about how to get a model, right? And we learned about how to get outputs from the model, and we showed you how it was easier to use Hugging Face pipeline feature and the Hugging Face hub to essentially use like different models, different AI models, as opposed to using like PyTorch to get outputs from them, and how Hugging Face makes it easier for us to use them. And then we talked about fine tuning. I apologize for the errors here. I fixed it in the morning. For some reason, it's back. But yes, so what we do when we are fine tuning is that we load the model, and then we basically get the data sets. We load the model, and then what we do is we get the training arguments, and then you get an evaluation metric, and then we define the compute metrics. We ask it to use we call compute to calculate the accuracy of the predictions. And then what we do is we call on like training arguments to define the evaluation strategy and the output directory. And then what we do is we use the trainer. We give the trainer the model. We give the trainer the train data set. We give the trainer the evaluation data set. And then we give it the compute metrics that we defined earlier. And then we use train on the trainer that we define. And then we can get what we have is the train model, and then we can save the train model. So that's essentially it. So that's basically it. Okay. If you have any questions, if you have any doubts, please ask him now. While you guys do that, I'll try to run again. I fixed it in the morning. I don't know how it's happening again. Okay, I will show you the guide by Hugging Face now. Okay, so this guide by Hugging Face has 3 parts. This is the part that we use right now. And sorry, this is the part that we use right now. Okay, and then now this part is for TensorFlow, right? So they have a TensorFlow version of the code to show you how to do